Thank you.
All right. And then let's see. Regarding our
Jackson Hole is presenting. Go ahead.
regarding our cargo system, we researched on how different planes lower their cargo based our design off that. We explored options for gently lowering cargo using either a hydraulic system or like a three cable system, which you can see in the top left of the slide. And then we explored those and we took pros and cons on each of them.
So we made some design matrices. Once we had a few ideas of what we wanted, we put them into our design matrix using some of our constraints. We just tested them how they would be against our constraints. As you can see with the telescoping legs, it came out as 4, 4.
Okay, so when you do a matrix like that, please put what is the best and what is the least. Okay, so in here, 4 is the best.
Yes.
Okay, just make a comment on that so we can always know which one is the best.
So for our legs, what came out was our telescoping legs with a 3.2, and then for our cargo system, our hydraulic system came out with a 3. Or the 3 cables came out with a 3.5 as the best.
And then so using our design matrices, we began to draw up our current design. So we're using telescoping legs with the added spring for controlled movement and shocks. We added a pulley system to contract the legs and be able to really like have full control of how much we can adjust them. And for the cargo system, we decided to just lower the entire rocket using that pulley against the spring that we have drawn in the middle here. And then it'll be able to gently lower the cargo system or the cargo payload.
Our current design is a telescoping leg, like she said, with the spring inside that will hold the leg and push it out with a constant force. And then we'll use a winch on the inside, which will pull the leg in to give it that needed adjustability for landing on uneven surfaces or just lowering it slowly. And on the right there, we have our for our payload, where we have on the top a ring, which will snap on the outside of the can payload. So we can attach to that without having to drill into it. And then on the bottom is something that we thought of to attach to, I guess, the second up can, which will hook onto the ring and keep it from falling out.
Mm-hmm.
And then on this slide is a more complete version kind of our CAD, except for we're going to make the legs a lot smaller because those are giant compared to the rocket.
Mm-hmm.
But let's see. Yeah.
So this is our current design, what we've printed so far. We've printed the ring that goes around, and as you can see here, it will go on our payload, and then it just kind of clips onto that bottom can. And then as you saw earlier in the CAD model, we'll have that little ring that or the little clip that will come down and clip it onto the next can of beans.
Then we had a few questions for you guys. So, like, what are some flaws that you see in our project that we might have missed just from like we didn't think about this one particular problem, or just like we think our problem's great, so of course it has no problem. And our second question was, what would be one thing that you would do differently?
Those are good questions. That makes us think. I'll just answer briefly, and then Dave, we need his input. What are the flaws you see in our project? I just want you to be really aware of the temperature that we're landing on. So, and The temperature on the moon is plus or minus a negative 200 or positive 200 degrees Fahrenheit. So you can build your model, which you've done. I like that ring, out of 3D printed material, but I need you to make sure you tell NASA what material to make it out of. And because it costs $1.2 million a kilogram to send something to the moon, NASA can make it out of the strongest and lightest material ever, because the transportation will be the cost. But I just want you to be aware that that is an important requirement, that you do some research on materials that would be strong enough, and don't worry about cost effective, because the transportation would be the cost really into sending anything to the moon. Does that make sense?
Yes.
Yeah.
Okay, let's see what Dave has to say about this.
Let me ask you first, what CAD program are you using?
We use Onshape for all of our 3D modeling.
Okay, so and I'm not that familiar. Is it a system that allows you to put some variables in and test them in the system itself?
You mean like a 3D like rendering type of thing?
Yeah.
I don't believe you can do any 3D rendering with Onshape.
Okay. So here's a question for you to investigate as soon as you can. You're talking about using a spring.
Yeah.
And the fact of the matter is, a spring is going to have some recoil to it, right? Where the idea here is you want something that is going to dampen this downward force when it makes contact with the lunar surface. So it looked to me as though you have already got some cans to build your fuselage out of, right? You've got your baked beans and your diced tomatoes, etc.
Yeah.
So have you thought about a specific spring that you want to use?
We haven't found a specific spring like online that we could buy yet.
Okay.
Right now, I have like kind of the idea that we're going to want a spring.
Well, one of the things I would suggest is your teacher probably has some of that material somewhere in the classroom. So I go on a scavenger hunt first to just see what you have available before you order anything on Amazon or go to Home Depot or wherever. Okay. Mm-hmm. The idea being, if you set up the 4 cans in the configuration that they're supposed to be for landing, and you drop those from 8 inches, little under 200 millimeters, right? Mm-hmm. How much bounce will a spring give you? Because that can become problematic. And I'm saying this from the standpoint that I've looked at a lot of other teams' ideas, and when they start this process, they begin to realize that once they drop this, they're getting a lot of recoil. And with every single bounce, you run the risk of the whole thing toppling over. And then when you add into that a 6% slope, that's going to compound the situation. So what I'm trying to get to is you want to do some basic testing as early as you can, just to see whether a spring alone is going to give you the kind of effect that you want, or whether you may need to add something into that. Okay? Shock absorbers and everything all have springs in them, but they're part of a system, and that system is designed to dampen, right? That's what you're looking for.
So Dave, before you continue, because I meant to ask this question this morning, are they taking that quick mix cement and actually making cement, or are they landing in a powder?
They're doing both, actually. According to the instructions now, right? You're supposed to pour about a 1 inch to 2 inch layer of actual concrete and let it harden. And
Yeah.
then you cover that with another layer of just the dry Portland cement powder.
Okay,
Correct?
I wasn't sure that they let the cement on the bottom layer harden. So
Yeah,
that
I think
makes a
it's supposed to
difference.
simulate both that surface of, the fine powder that we know exists, but underneath it, it's probably pretty dense and hard.
So is this the project he said to put he put flour on it? Instead he was putting cement, and then he changed it on his newest things to flour.
I haven't seen anything about flour, so maybe there's an update. Are you guys familiar with that?
Did you see the updates? He puts updates.
Yeah, I
Yes.
checked sometime this week when we were told it was updated, but there was
Mhm.
nothing about flour. It was just
Okay. It could be a different one. But if you're doing cement, I don't want you to breathe it in, so
We
that you wear your mask and your gloves when you're
Yeah,
doing the powdered cement. Okay.
right.
So that's why he changed one of them to flour, because why use cement if you can use something that isn't dangerous to breathe in? But I
Right.
can't remember which project it was exactly.
The other comment that I wanted to make, team, is once you render this in a 3D print, you need to consider how you're going to attach this to that bottom can before the payload, right? It's going to have to be pretty robust,
yeah.
right? I mean, my sense is a lot of people have thought, well, we can kind of hot glue this or maybe epoxy it, and I'm not convinced that that's going to be enough. You're probably going to have to actually drill holes and bolt this thing onto that. It doesn't seem like a lot, but when you're dropping this, there's a fair amount of mass there. It's going to have a lot of force applied to it.
Mhm.
So again, my suggestion is you've got lots of time to work with now, but what I would do is look around and just see what kinds of materials you have right on hand right now that you could just do some basic testing with. See how springy those springs are, how much recoil they are going to impart on this system. And then you can look for things that will try to modify that.
Mhm.
Okay?
Okay.
That's good. Good advice.
Yeah.
So
Otherwise, I
that
like your
kind of,
design. You've got a lot of good components to this.
yeah. So that really answers your question. What would be the one thing you would do differently? And that would be testing, looking around, trying to get different springs and testing it. And I recommended to another school. I might have mentioned it to you guys about Vulcan springs, because there's all kinds of springs out there that can help you. And
Mm-hmm.
and a lot of springs are used in space. And though this rocket is going to land in space with 1/6 gravity, as Dave pointed out this morning, it's still, your testing still has to land on Earth. So your testing is going to be for Earth. That spring has to work for
Yeah.
your rocket now on Earth.
Right. Can you talk for a minute about the system or the method you want to release the payload from the rocket?
The payload release right now on that ring design, we kind of just had,
A hook.
yeah, we had the
There
hook,
we go.
which would
Okay.
be attached to the can above the payload,
Uh-huh.
and it's not CAD on the ring yet, but on the ring there would be like,
Sure, sure. No, um, so how will that hook be released? Is this going to be done manually by you with the idea that in the future we can come up with a more mechanized system?
Maybe we could probably figure out some sort of design with like a servo, or maybe like hook up a string to each one of them. And
Yeah. And here's the reason that I'm asking. From the beginning of this project, the title of the project itself suggests that we're focusing on landing legs. That's a big piece of this, but the whole strategy behind this entire design is having the payload at the bottom of this rocket versus what SpaceX wants to do, which is put it way up at the top, which is kind of crazy. I mean, even an astronaut climbing out of that rocket and having to come more than 100 feet down to the surface is nuts, right?
yeah.
So if we can convince NASA that this is a plausible system, it has to include an effective way to release and kind of gently release that payload to the bottom. So with that in mind, understand that we're going to have a lot of teams working on all sorts of different legs, but we also have to take into consideration that payload delivery. And when it comes to the CDRs and selecting teams as finalists, I suspect that we're going to see a lot of really good legs and, at least some good payload delivery. We'll probably select a couple of teams just because they came up with a very innovative way of putting this stuff onto the surface, right? So what you have there is a mechanism, a system I haven't seen before. Nobody's come up with anything similar to that yet, which means you're working in a pretty innovative area. Now, if you can find a way to improve that design and make it a very effective one, that alone might end up being a reason that we would select yours as one of the finalists.
Mhm.
Does that make sense?
Yes.
You got to understand with every project that we put out, there are lots of parts. And we look at the entire project, but we focus on each individual component. And we will ultimately want to take the best design for each component and add them together to make the best system that we can, right?
Yeah.
So this is just a long-winded way of saying you've got an innovative idea there. It has potential. So focus on that part as well.
Mhm.
Who
No,
knows? That could be a deciding factor for your team. Okay.
yeah, that's important information. Thank you, Dave. That's really good. And the other thing, when I looked at that little hook, I thought of, hey, you could have two ways to do that. You might have some kind of servo or actuator, but you could also have a manual. And NASA loves redundancy. Hey, if the servo doesn't work, we can have an astronaut do it by hand.
Right. So, team, here's a thought. This is an area for you to maybe research. NASA has what they call a universal end effector. It's what is used on the end of the Canadarm for the space station, and it allows for that system to attach and release to all sorts of different shapes and sizes of equipment. So rather than going with a highly technical, one piece is designed to do one job, they've come up with a more universal way. Take a look at that design because you may be able to incorporate something like that into this release mechanism, and it would be very analogous with what NASA's already doing, right? So just look at the Canadarm on the International Space Station and look at that end effector. Okay?
And what
All
was
right.
that? The end effector?
It's called I may be stating that a little incorrectly, but if you look up Canadarm and the method that it uses to grasp and release items, you'll see how that mechanism works. It's
Okay.
actually brilliant. It's simplistic in design, and it allows you to pick up all sorts of different shapes and sizes, etc., with just one effector.
Wow.
Okay?
Do that.
So check it out.
Thank you so much, Dave, for that information.
Yeah, you bet.
All right. So did you have any other questions, team?
I think those are all that we had. This is all a lot of great info, and we've got a lot of research to do. So thank you very much.
All right, very good.
Well, thank you so much.
Thank you for your time.
You enjoy the afternoon there. Bye-bye. That's Jackson Hole, Wyoming. All right, and so we're going to go all the way from there to Olympia, Washington. Thank you, Dave, so much for joining us.
Sure.
Your input is incredible.
Is the audio working?
Yes, we hear you fine.
Hello.
Hi, introduce yourselves. And so there's two teams, right? Two separate teams. Okay.
We are the first team. My name is Diego.
I'm David.
I'm Oliver. And so we don't have a slideshow today, but
that's okay.
We do have a more or less a 3D printed model of kind of the design that we want to go for the leg. It might be a little bit hard to see, but we want to try and have it on the side of it like this. Obviously, it's going to be longer when we do our actual prototype, and we want to have it probably 3 to 4 legs we were talking about. We want to also try and have the suspension, so it would land right here and the suspension on here, and the parts here and here and here being flexible.
So, hey guys, you've got a couple of different screens there, and basically my screen's showing the tops of your heads and a roof. I'm not seeing
yeah. I pinned them, so you can pin the one that says, let's see, anything different. Yeah. It just has his face, and I don't know if you can find the right one to pin.
Should we try and just do this with one camera?
There we go. Go.
Yeah, do you got them?
Yeah, so David's right in the middle of the screen. So maybe if he holds the prototype, we can see a little bit better. Yeah.
Okay. So that's, yeah.
Yeah, that works.
Okay,
Perfect.
and then for what we wanted to do, in terms of attaching the prototype on, we curved a piece of metal to put around the center can, with the can on the bottom being the payload. So we're just trying to make it easier for us to attach it. Those rubber bands is just us mainly playing around with the idea of the payload delivery and how to latch it onto there well.
Sure. So is the can that's wrapped around the bottom? Is that the payload can itself?
No, this can here is
okay. That's what I'm clarifying. Okay,
it's
so
not
you've
attached.
got perfect. So talk for a second about those rubber bands you have attached there. What are those for?
Our original idea was to have it on like this, with something on the bottom to attach to the bands, so it would be kind of depending on the length or the size of the payload, you could change the length of the bands to accommodate for the different sizes.
Okay.
So I think that was our original idea. We also had a few ideas with having the latches more on this part around here and not having anything on the bottom of the payload.
Right. So here's a thought. back to your leg attachment. Uh, I'm assuming that part of your reason for putting those pieces of curved metal on there is to help reinforce this, right?
Yeah.
Okay. So that particular can is going to be empty. That's also where your mechanism for releasing your payload could potentially be stored as well. So given the fact that there's nothing in the project description that describes whether you can or cannot add anything to the outside as you have done, I would suggest that you send an email to Glenn Johnson and with a picture of what you've got there and ask him if he's okay with that.
Okay.
Now, if there is a concern that we're kind of increasing the diameter of that stage more than necessary, you could potentially put those curved pieces on the inside of the can, right? Mm-hmm. And that would give you a little bit more thickness with which to, maybe drill some holes and put a bolt through there to attach the legs with. Does that make sense?
So from my understanding, the can that we're having the legs attached to, we can put anything inside of it and any holes in it.
You absolutely can.
Okay.
Yeah, absolutely. That part of the reason for making that can empty is because we understand you're going to have to come up with a pretty secure way of attaching those legs.
Yeah.
Gluing them isn't going to be good enough, right? So you're probably going to drill some holes through there and put some nuts and bolts or something analogous to it that way. And that's perfectly okay. And if you want to add that extra layer, that curved piece that you did, by the way, you did a nice job of fabricating that. You could put it on the inside as well as the outside, right?
Yeah.
So again, the only thing is I would hate for you guys to keep moving forward with your design, and at some later date, Glenn comes back and says, "Nope, you can't put that extra layer on the outside." Right? I don't want you wasting your time. So send him a picture of that with what your design idea is, and just find out if he's okay with that. You don't have to change a thing.
I think just knowing that we can put stuff inside of the can is really helpful because part of the
Absolutely.
reason why we wanted to put the the metal bit around it is just so it'd be easier to attach the legs onto it, but knowing that we can put stuff inside is very helpful.
Yeah, absolutely. And
Yeah.
the reality is if you think about it, on a real rocket, it would be extremely aerodynamically challenging to try and have something on the outside of that fuselage that is a mechanism for releasing the payload, right? I mean, we got to launch this thing, right? And it requires some very specific aerodynamics there. So generally speaking, you want to internalize things as opposed to having them out on the outside. And with that can being empty, you can utilize that space for any kind of mechanisms that you would want to use. So similarly, those straps, those bungees that you've got there, you could attach those to the inside as well, right? For sure.
Okay.
And actually, don't throw away what you did, because that is that outside. You could explain. We can't see if you put stuff on the inside. We can't see it so well, but you already have what you're thinking of putting on the inside, and we can see it really well. So you can. That's a really good part already done for you, because we need to be able to see what you're thinking, and so the outside work. And also copy me. I need to.
Yeah, and guys, again, I just don't want you. I don't want you wasting your time, right?
Yeah.
So take a picture, send an email to Glenn, copy Flo on that, But when you send it, just say, hey, at the PDR, Dave from Colorado said we should check with you to see if this is okay.
Okay.
If he comes back and says, I'm fine with that, then just keep doing what you're doing, right?
Yeah. Yeah.
Thank you.
And he might, who knows?
Yeah.
Because I actually sent him an email similar where I said, can they put their mechanism for releasing their payload inside or outside on the bottom of and he said either way worked.
Yeah.
But that's a little thing. This is way bigger. So check it out.
No, you got some interesting ideas there. Go back to your leg for a minute. Talk to me a little bit about how this is going to work.
So obviously this is a very small model for it. It's not two size, but the idea was we wanted it to be on here like this.
Okay.
It would extend farther out. The idea was whenever it were to land, it would have like a bit of laxity to it so that it wouldn't just, and also like having on the hinges right here to have some,
Okay, so that was my question, because on that piece you printed, that V at the end is a fixed joint, right? That's going to be static.
We want it to not be static just so like it's not frail and it will break because
Right. Okay.
so
Okay.
it's going to be also this will probably be made out of metal for our prototype. And we also want to have the suspension on this part right here so then when it lands it'll be able to move upward like this. So but also have enough resistance that it wouldn't bounce or it wouldn't
Sure.
or yeah.
Right. Well, so here's the thought, guys, because you've already got you've got your rocket body there already, right? And I assume that each of the cans that have material in them are still there, right? So you have the right mass to work with.
We do.
I think just for grins, you should find a way to attach those legs on there now and just drop this.
Okay.
One of the things is if you do this and you video that with your cell phone, you probably got a slow-mo feature on your video, and you can go back and slow this down enough to kind of see what's actually happening at those attachment points, et cetera, that might give you some sense of, okay, how much flexion do we need, right? I kind of like the way you're going with this because, again, I've seen a lot of designs where people are relying on basically on coiled springs. And springs alone are not going to dampen this landing. In fact, what's going to happen is you're going to have a pogo stick. This thing is going to go like this, right? And every time it hits, it has a risk of toppling over, which is what we're trying to prevent. So, give it a couple of goes right now. Just drop it on a flat surface and see what happens. That'll give you a sense of just how much flexion you need to add into this to control it.
Okay.
Now, our test design throws in that wrinkle of a 6% slope, right?
Yeah.
Which means that inevitably one or two of the landing legs are going to make contact before the others on the opposite side. And that can be enough to start this thing tipping. So it does need to have some ability to absorb this without, kind of toppling your rocket body over.
Yeah, we have the slope actually concreted right now. Yeah.
Okay, great.
Oh, good.
Yeah.
Right.
I did have a question though about regarding the truck and the
Sure.
pad. So is this going to be like on the bottom, or how is this going to be?
No. Let's go to that rocket piece.
Okay.
Okay.
This one?
No, to the piece you printed.
The blue circle.
Yeah, the blue. Yeah.
This piece?
Yeah, exactly. That's actually supposed to simulate the thrusters. So that goes on the top of the rocket.
Oh, okay, I see.
Okay.
Just
So
Like,
you can see that groove,
the,
right? That's there. That's actually supposed to
that's
nest
right.
right into
oh,
the
okay, I
top of
see.
that can. Because again, our whole strategy with this is move the thrusters from the bottom of the rocket to the top and move the payload from the top to the bottom. We're inverting everything here. But again, you know, when you look at those images, like Glenn's got one on the website for your project now that shows one of the SpaceX rockets. That's basically the design they're going with right now.
Okay.
This thing's going to land on the surface. That rocket is over 100 feet tall. So you've got a crew cabin. First of all, you've got astronauts that have to get out of this rocket and come down, 100 feet.
Yeah.
And then you got to unload all of your payload and bring it all the way to the ground. I mean, that's crazy in my mind, but that's just me. We're trying to convince NASA to go with a different design idea with this.
Okay.
Okay.
So,
Now, did you have another question about
about the car. So
uh-huh.
Where's this going to go? Is this
Okay, that replaces the payload on the bottom.
okay?
So in the two tests that you're doing, you'll land once with a can of beans, which is your payload, right?
Yeah.
In the second test, you replace the can of beans with that LTV.
Okay.
Okay. So it's going to be attached to the bottom of this as well.
Okay.
It
Thank you.
just replaces that bottom can of beans. Make sense?
Yeah.
Okay.
So there's like 3 projects here: the legs, the cargo can of beans, and then the little vehicle delivery. 2 different deliveries and the lakes. It's a lot to do, guys.
Yeah, but in reality, you should have one delivery system. You should have one mechanism
That can
that will
deliver.
allow you to release that bottom level of your fuselage, the can of beans, or something like that LTV on the bottom.
Yeah.
Okay?
We have this little thing that
Perfect. You got go
which
with it.
we're
If you
gonna
want
have
to do that,
test
that's
on.
fine. That's perfectly fine.
Yeah, that's good. Yes, remember keeping it light as possible.
Yes.
So that's cool.
Okay.
All right. All right. Let's, if you do, you have any other question, or can we go to team 2?
Yeah, I think we're good.
Good.
Okay.
Thank you.
Thanks,
And you
guys.
can always ask questions, but send that one question to Glenn. Just copy me. Thank you so much. Enjoy the afternoon.
You too. Thank you.
Yeah. All right. Here's team 2 at, thank you, Dave. Great job. I really appreciate your input. Hello, team 2.
Hi.
Hello. Hello.
Can you
Hi.
Good morning, guys.
microphones over here? How are you guys?
Doing well.
Good.
All right, can you hear me?
Yes,
All right, so we're team 2.
but we don't see you. You're in between the two cameras. So
Okay. Yeah. What? Yeah, turn this one off. Turn this one off. What is going on? All right, there we go. He's with the camera. Then, yeah. There we go. You can see us all now, right?
nope.
No? Dude. All right. Hey, scoot over one.
Just get
yeah.
them together. Get on one
Yeah,
camera.
there you go.
All right, all together, guys. All right.
One of you is right there in the.
Get over
Here
here.
we go.
Yeah, one's in the center. Oh, there you go. All right.
The microphone's on the back. Okay. Okay, so we are designed right here. It's the
Oh, good.
block on top, and then the can, and then the payload at the bottom, which is this can of beans. And then
Mhm.
at the bottom here, we have this cardboard ring right here, which we were using to kind of attach the legs to. Like here's a leg design that we printed out so far, and we're planning to put it like right here on the can.
Okay.
But it's only our first prototype. We have a few ideas, and then also we have the rover here.
Okay.
We have a few ideas, so we have papers, but I don't know if it's that easy to see on there. So we did scan.
So actually, the main screen I'm seeing is just the back of your shop. You've got at least two different cameras going.
Is this
Yeah,
one?
yeah, I can see you now.
All right. So,
All right, yeah. We each have one camera for each person. So
all right. Can you see what the designs are? No, you can't really see
Yep.
that.
Sort of. Yeah, I can see
Yeah,
the
we
page.
can see it.
Uh-huh.
All right. Well,
Well, are you
I'm not sure.
Okay.
We have scans of it though, so we could like screen share that.
Yeah, you can screen share.
Let me share my screen.
But we don't really have too much for the prototype, but we do have the concrete like all poured.
Okay.
And we do have a lot of like me and my team brainstormed a lot and we put it down on paper. We're just like our main issue is like trying to figure out like materials and the way we're gonna dampen the landing.
Okay.
All right, so here was one of our first design ideas is that it's kind of rough, but we were planning to have like two of these rings right here, like a ring here and a ring here, and the legs come off this second ring. This original design, this ring was supposed to like slide up and down with like shock absorbers right here. So this ring would like, as the rocket,
Okay.
this ring would move up and the shock absorbers would absorb the shock.
Okay, so here's a question. Given the fact that you're going to land on a 6-degree slope, one side is going to make contact before the other, which means that one side is going to get pushed up before the other, right? Now, is that ring going to give you the flexion you need for that to happen?
We had an idea for that. I didn't write it down anywhere, unfortunately.
I remembered it.
Oh, okay.
All right. So we were thinking that maybe we could have some sort of like sensors in the legs where like as soon as it touches down, it like releases, I don't know, like some sort of mechanism in the other leg, allowing it to extend a little bit so I can catch it before it's all out of angle and such. But we're not entirely sure on how that would work since we're trying to figure out how to like get on a smaller scale.
That sounds really complicated, guys.
Yeah. That's
Plus, think about this. The time differential is going to be, in like hundredths of a second.
Yeah.
For something to even sense and then send a signal to, start that compensation, I think you're over engineering here.
Yeah, that's what I was thinking. That's why we sort of scrapped that first idea and focused on like the like base design of this like actual legs until we could like brainstorm better ideas for it. But that's just what we had for the dampening.
Well, I guess what I would encourage you guys to do is you've made a cardboard ring. Is that what that one that you had?
Yeah.
Yes.
Okay. So you're actually going to have two, right?
Yeah.
The bottom one is going to be able to move.
Yes.
Okay. Test it. I would find a way to just, to attach something to just simulate the legs without even worrying about, whether the legs flex or anything like that. You're trying to test, first of all, the efficiency or the efficacy of that ring moving up and down. So attach something. They could just be straight pieces of plastic or doweling or something like that, and drop that a couple of times and actually see what happens, right? See whether you get that motion in there that you want it to have. You might be able to design it to do that.
Yeah.
Yeah, the only issue would be obviously the angle at which we're landing, because River, can you pass me the
of course.
Because we do already have our cement poured
Perfect.
with the 6-degree angle here, but somebody step in it, so there's kind of like a divot right here, but otherwise this will be our.
Hey, that looks fine, guys. That totally looks fine.
The only issue we have with the footprint is that it like pushed the concrete out, so it increased the angle, and we're wondering if that was okay.
I think right now for testing, go with it.
All right.
Yeah. But again, here's the thing. I'm a big proponent in testing, right? It's great to know physics and understand theoreticals, if this, then that, but nature doesn't always work that way. In fact, most cases, it doesn't work that way. So you got to test it. And don't be afraid to fail. Don't be afraid to break this, right?
Yeah.
I mean, you've got a novel idea here. I haven't seen anybody else come up with anything analogous to what you're working with. So give it a go and see what happens with this thing. Like I say, I wouldn't worry about, trying to build this up and make it too technologically sophisticated right now. You just want to know whether that ring is going to move and dampen the way you think it does.
All right.
All right, and then we had one more. This is what my friend River has designed, and
Most of it doesn't show.
and it's since the scanner didn't really pick it up that well, but this was like some he design. I'll let him explain it.
Uh-huh.
I was just like some thoughts I had from like looking at the other like Apollo missions and such.
Mm-hmm.
And I was just thinking about like it's just idea that I had, like having it flex a little bit to help dampen and such. Some thick joints, like I shown. Like, could you
No, I can. What do you want?
This part right here, like hover over. Like,
well, you just made a statement that I think speaks volumes, right? You're talking about varying the thickness of each part of that strut. The thinner it is, the more it's going to flex, right?
Yeah.
And that is probably a good direction to be going, right? As opposed to, building hinges and pivots and a number of different things. Just think about the materials that you're using and the amount of flex you have in it, no matter what it is. I mean, think about it. Even concrete bridges are designed to flex. Yeah. They have to give. So I think you've got a good idea there. I would test that out. Were you thinking about printing this in a plastic, or were you building it out of something?
So we're gonna
we do have a plastic leg right here.
But for this idea that's being shown, I believe that we were thinking about like trying to build out something, since with our printers, I think it would be a little bit too fragile. But I think we could print out some stuff to test like the physical flexing of materials and such.
Sure.
What we want to do.
There you go. And again, I wasn't advocating, a 3D print versus something else. That's entirely up to you. But again, it's that whole idea of this is kind of like material science, right? Mm-hmm. Look at these different systems, a thin sheet of aluminum or plate metal or something. There's a lot of bend and flex that goes into that. And you can get a lot of absorption just from that alone.
Yeah.
So I would try it.
All right. And then our last thing we had to share was the HUNCH or the CAD that we've designed for it.
Uh-huh.
So here's obviously the cams, and then the ring right here, and then this was supposed to be like how you lift the payload or drop the payload to the surface.
Okay.
Of like some sort of scissor, like the scissor.
Sure.
That lift people up. We're thinking something similar, and that will just lower it down. But obviously, it's we can't really do it on a small scale. So
Well, I bet you can. Again, when you start thinking about the right materials, I think the real significance of this is, um, if you design your legs to have a certain length that allows that payload to get close to the surface, right?
Yeah.
So that, you need to have enough space there for these legs to flex and not have the bottom of your payload smack the surface.
Yeah.
But you don't want it to go much more than that, because all you got to do is make a separation between the payload and the rest of the body of the rocket. Doesn't have to be great. In fact, the less it is, the easier it's going to be to drop that payload effectively.
Yeah.
Yeah.
Right?
So in our current design, we do have a small gap between the bottom and where the legs are.
Exactly.
But then it's this part right here. So either we need to make the legs shorter, or we just lower it down this far and have this like where the legs, and then this.
And the only way you're going to find that out is to test it.
Yeah.
you got to drop this a few times.
Yeah. I mean,
And I would keep the gap on the bottom, because what if that payload can is right on a rock?
yeah,
Exactly.
If it
Exactly.
lowered down, then this would be like this segment right here would be right here, so it'd give it an extra.
Yeah. And I like that scissors in the. I forget, there was a project last year. They actually redesigned the, when you go to Lowe's and it has those those ladders that kind of look like a scissors and it goes up and down. And a team, it was this summer. They redesigned that. They re-engineered it. And they had to do a big thing. You only need like two little, you just need a much smaller thing. But they had actually bought something and took it apart. Yeah. So that's a good middle thing to help, if they do hit a rock, you have that in also.
Yeah.
Exactly.
All right.
Nice job, guys.
Thank you.
Yeah,
you've got
really nice.
You got some great ideas here. You really do.
Yep.
Thank you.
And I was even thinking, I don't know, this kind of crazy, but maybe you have two legs on one ring and two legs on a different ring.
Oh, that would work. Yeah, I can see that.
They move independently.
Yeah.
Okay.
So good.
Thanks for the idea.
Yeah. Any other questions?
I don't think so.
All right. Very good.
Excellent.
Thank you, guys.
Thank you so much. Good
Thank
job. You enjoyed the afternoon there.
You
Thank you, Dave.
Okay.
Thank you so much for joining me.
You're welcome.
You really, really helped. Can you join tomorrow?
Tomorrow should work better for me. Yeah.
So I have the first team tomorrow is back to Bozeman, and hopefully you'll be able to come to MSU for the critical design review. That's going to be February the 18th. Are you busy then? Do you know?
Hang on. I'm looking at tomorrow right now.